In this module, we introduce you to vectors and the manipulation of vectors. So vectors are essential in the study of electromagnetics, which deals with vector quantities. We are used to deal with non-vector quantities called scalar quantities, but there are a lot of quantities that are vector in nature. So these are quantities that have both magnitude and direction. And these quantities are usually found in the fields of solid mechanics, fluid flow, heat flow, and other fields in engineering. Vectors are also the basis in the design of systems such as airplane, generators, and even robots. A scalar is some specific value without any direction of some sort. A scalar field, however, is a function that gives a single value for some variable in every point in space. An example of a scalar and a scalar field are voltage, current, energy, temperature, and length. So these quantities does not need any direction to be defined. So a scalar field is a quantity solely determined by its magnitude, and there's no direction whatever. A good example of a scalar field can be found by mapping the temperature, let's say, of a country. So here we have the temperature on any location in the United States, and this represents a scalar field um, showing the temperature in every location. A vector field has both magnitude and direction in space. So a good example are the velocity, quantities, momentum, acceleration, and force. So for these quantities to be meaningful, it is not enough to have to define them as having a magnitude, but of course a direction as well. An example of a vector field is the jet stream that can be found here. So in here, at any point, at any location in this map of the United States is defined, is shown as the velocity of the jet stream. So at every point, there is a magnitude and a direction as well. So let's say in this point, the magnitude is given and it has a certain direction. And let's say at this point, it has also a magnitude and a specific direction. Another example of a vector field is the gravity that we have in Earth. So the direction of this field is obviously towards the center of the Earth, like that. Here we have another example of a vector field. This one represents a faucet where water is sprinkling out, and the velocity. For example, we take this point as an example. It has a specific velocity there and a direction. Here, maybe there is a velocity as well, and this is the direction. So it represents a vector field. Another example here is the circulating flow of particles. So we have a cone here, and there is a center, and let's say the particles are moving around about the center. So at this point, it could be that there is specific velocity of those particles there, and it is directed somewhere there. Here we can have another, we can pick up another example, and it has a certain speed there and direction. So again, this represents a vector field. So a vector quantity has both a magnitude and a direction. Now sometimes the size or the magnitude of a vector is also referred as the vector's displacement. The magnitude is also is considered the scalar portion of the vector and is represented by the length of that vector. Direction indicates how the vector is oriented relative to some axis. Vector quantities can be represented by a variable with a bar above the variable. Sometimes other uh, representations show this as a variable with an arrow above directed to the right. One way to show the magnitude and direction of a vector quantity is to write the vector quantity in this manner, where this one, uh, the vector quantity with two vertical bars, represents the magnitude of the vector, and beside it is a vector called a unit vector, where the magnitude is unity or 1, and its direction represents the direction of the vector quantity. So the small letter a here is a unit vector that has the same direction as the original vector quantity. Now graphically we can represent a vector by an arrow, where the length of the arrow represents the magnitude of that vector, and the direction of the arrow is represented by represents its direction. So the length here is this one. So the vector quantity enclosed by two vertical bars, and the direction is represented by this, which is a unit vector with a length that is equals to 1. So the length of this is equals to 1, and a direction that has the same direction as the original vector quantity. To differentiate between a scalar and vector quantities, um, we usually represent vectors by a bar on top with a variable with a bar on top or an arrow, um, and represent scalar quantities with just simply a variable without any bar or an arrow on top. Sometimes we also represent a vector quantity with a variable that is written with a boldface type, and those variables without that is not boldface simply means that they are scalar quantities. Vectors can be manipulated, meaning they can be added, subtracted, or multiplied. There's no such thing as division of vectors. We can multiply a vector with a scalar quantity, and the result is another vector with a magnitude that is equals to k times the length of the vector, and with a direction also the same as the vector. And we can write that in this manner. So this is a vector that has a length k times the magnitude of the vector, and beside it is a unit vector that has a direction the same as the vector quantity. There are two types of vector multiplication. We have the scalar or dot product, and we have the cross product. A dot or scalar product is written as the two vector quantities with a dot uh, in between them, while a vector or a cross product is written as two vectors with an x or cross between them. A scalar product or dot product of two vectors always yield a scalar with a value equals to the product of the magnitudes of the two vectors times the cosine of the angle between the two vectors. Now, the angle should be chosen as the smaller angle between the vectors. To get a better understanding of the dot product, so let's say we have here two vectors. So here we have A directed to the right and vector B here, and we multiply the two using the dot product. Now this can be interpreted as something like this. So we get the, let's say, the projection of the vector B along the direction of vector A. So this is the projection of B along the direction of A, and that is equals to this one. And then we simply multiply this projection with the length of the vector A. So that will give us something like that. Or we can interpret it as getting the projection of vector A along the direction of vector B, which is this one, and then multiplying this projection with the length of vector B. And you will get that result. And notice that these two results are just the same and equal. So always remember that a dot product always returns a scalar quantity. The dimensions of vectors involved in a dot product must match. Sometimes we use the dot product to compute for the angle between the two vectors. So we can state that a dot product of two vectors is equal to the component of the first vector that is in the direction of the second vector multiplied by the magnitude of the second vector. But as earlier shown, it is also equal to the projection of the second vector in the direction of the first vector times the length of the first vector. A good example of a physical phenomena that uses the dot product is when you, for example, push an object with a force that is in that direction. So we have a force F there, and it displaces by this amount D. So in this case, F here and the displacement are both vectors, and both vectors are separated by this angle. You'll notice that if we compute for the work done by that force, okay, work, uh, that would yield something like this, which is really the dot product of the force applied on the object and the displacement of the object. So therefore, we can write it this way. Okay, dot product adheres to some of the manipulation laws in algebra. So it satisfies commutative law or the commutative property, associative, and also distributive property. Now let's go to cross product. Another name for cross product is the vector product, and a cross product of two vectors always yields another vector. So let's say we have two quantities, vector quantities A and B. When we say A cross B, so here A cross B, that really means that we are trying to get another vector with a magnitude that is equal to this. So the magnitude of vector A times the magnitude of vector B times the sine of the angle, the smaller angle between those two vectors. Now, the direction of the resulting vector would be the direction of a unit vector, which is really the direction based on the right-handed screw. So, for example, I have a screw and I turn the screw in the direction from vector A to vector B. Whatever the direction of that screw will be the direction of the resulting vector. So the way that the vectors in a cross product are written, the sequence on how it is written, should be observed. That means that A cross B is not the same as B cross A. In fact, A cross B is actually the negative of B cross A. So this is a graphical representation of the cross product. So let's say we have here A cross B that will give us a vector which is like this, and that vector is perpendicular to the plane of the two vectors. So this direction is the same as, let's say, when you turn a screw from the direction of from the vector A going to vector B, like that. So that will result in the direction of the screw uh, going upwards. However, if you want to cross product B times A, well, the result of that would yield a vector that will look like that, which is also the same in the same magnitude as this one, but in the opposite direction. So so this one is actually that vector. So remember that a cross product always returns a quantity, a vector quantity, not a scalar. Now the two vectors in the same or opposite direction will always give you a zero because the sign of at 0 degrees or sine of 180 degrees, in which case you have two vectors that are in opposite direction will always give 0. Also, the magnitude of the cross product of two vectors, you will notice that it really represents the area of the parallelogram that results when you draw the two vectors, and the direction will always be perpendicular to both of the original vectors, and the direction will always follow the right hand rule. Now, vector product or cross product uh, does not follows the commutative rule. So this product is not the same as that product. It is in fact anti-commutative, as I mentioned a while ago. So A cross A results in a negative B cross A. It is not associative. You cannot say that this one is equal to this, but it is distributive. So this one is equal to that. We can multiply three vectors. So for example, we have here three vectors, and let's say we have B cross C, and the result we dot product that with vector A. So that means that this one will give a vector and dot product with another vector that should yield a scalar result. However, if the result of B cross A is cross multiplied by another vector, that will give you a vector result. Now, the question is, let's say I do this, let's say I cross it with this one, okay. Now, this one will yield a scalar result, and the question is there such thing as a vector cross product with a scalar? Well, we haven't explored this one, and this is an open question if such product exists or applies to some phenomena. So important notes about vectors. So when writing a vector, always represent it by a variable that has a bar or an arrow on top of it, or else it might be mistaken with a scalar quantity. Do not add or subtract vectors from a scalar. There is no such thing as division of two vectors, so do not attempt to do division. Now, two vectors are perpendicular to each other if their dot product gives 0, because that means that if they are perpendicular, their angle is 90 degrees, and cosine of 90 degrees is 0. Now, if you want to know if two vectors are in parallel, all you need to do is get their cross product. And if yields 0, that means they are in parallel.